Welcome to the Era of Agentic Organization, learning to organize with language models. The big idea is simple. Instead of treating a model like one brain thinking in a straight line, we let a team of small specialist minds coordinate, like a well-run crew. Agentic organization means the system doesn't just think. It organizes how to think. It decides who does what, in what order, and when to regroup. Why is that exciting? Because many problems aren't just hard, they're decomposable. If you split them smartly, run the pieces concurrently, and stitch the insights back together at the right moments, you can be faster and more accurate than any lone reasoner. This paper proposes a concrete way to do that with language models, turning free-form reasoning into a structured, collaborative process that learns to manage itself. Asynchronous thinking, async think, turns reasoning into a living workflow. Picture a project manager, the organizer, and a set of specialists, workers. The organizer breaks the question into subqueries, dispatches them to workers, and, as partial answers stream back, merges and redirects effort. Crucially, workers don't wait for everyone to finish. They run concurrently, and the organizer adapts in real time. This is different from plain parallel thinking, where you launch several independent solutions and only combine at the end. Async think collaborates during the process, not just after it. Under the hood, the how to split, when to fork, when to join policy is learned with reinforcement learning, so the system improves its own orchestration strategy. Why care? You get both speed and quality. Experiments show about 28% lower latency than parallel baselines, while also solving math problems more accurately. Even better, the learned organizing habits generalize, so the system can tackle new kinds of tasks without retraining. The figure contrasts three mental models. Sequential thinking is the single-threaded monologue, one step after another. It's safe but slow and brittle. Parallel thinking spins up many separate solution paths, then votes or aggregates at the end. Faster, but those paths don't talk, so they duplicate effort and miss chances to help each other. Asynchronous thinking adds structure. A coordinator can fork tasks when it sees natural subproblems, let workers run concurrently, and then join results when enough evidence accumulates. The arrows aren't fixed. The organizer decides them on the fly. Think of it like a newsroom editor assigning breaking stories, pulling reporters back when a lead is cold, and merging drafts into a single article. Concurrency with coordination. That's the unlock. The key distinction is where collaboration happens. In parallel setups, collaboration is postponed. Independent traces run to completion, and an aggregator merely combines final answers. That wastes time on dead ends and can't exploit mid-course corrections. In async think, an organizer actively shapes the thinking process. It decides when to fork a subproblem, when to pause or stop a branch, and when to join partial findings to guide the next steps. This lets the system cut unpromising work early, reuse intermediate insights, and reallocate compute to what matters. The payoff is lower latency and better accuracy, especially on multi-step tasks like math, where early lemmas can inform later moves. It's the difference between tallying votes and directing a team. Welcome! This paper introduces async think, a way to make language models reason like a coordinated team rather than a single, overworked brain. The big idea: treat thinking as an organized process with roles, schedules, and mid-course coordination so the model can split work when it helps, merge results when ready, and keep moving without waiting on the slowest part. Think of it as taking the best of human organizations, managers, and specialists, and building that logic directly into how the model thinks. Here's the motivation. LLMs are great soloists, but complex problems often need a band. Agentic organization means multiple minds collaborate, not chaotically, but with structure. Who does what, when to split a task, when to regroup. Current systems mostly run several independent thoughts in parallel and combine them at the end. That wastes time, you wait for the slowest, and loses opportunities to share partial insights midway. The vision here is a model that can plan its own internal teamwork, deciding when to divide and conquer, when to go step by step, and how to sync across parts so it handles a wider range of problems more efficiently and more reliably. Three big hurdles. First, latency. Naive parallel thinking is like launching 5 separate essays and waiting to grade them all at once. You're bottlenecked by the slowest essay and an extra aggregation step. That's wasted time. Second, rigidity. Fixed workflows don't fit diverse questions. Some problems scream for divide and conquer. Others get messy if you split them. If the system can't adapt its plan on the fly, you pay either in speed or accuracy. Third, who designs the plan? Handcrafting the right coordination for every query is impossible. We need the model to learn organizing policies, when to fork tasks, when to merge, how to route attention, rather than follow one-size-fits-all templates. In short, reduce waiting, increase adaptability, and learn the playbook automatically. Async Think turns reasoning into an organizer-worker protocol. Picture a project manager, the organizer, who can fork to create subqueries and assign them to workers, then join to merge results when they're ready. Workers think through their sub-questions and hand back intermediate knowledge, not just final answers. The crucial bit: everything runs asynchronously. Some workers finish early and feed insights back. Others take longer. The organizer can spin up more workers, pause, or consolidate. This flexibility lets the model choose the right execution shape for each problem: short pipelines, branching trees, or hybrid schedules, so it can move fast when possible and collaborate deeply when needed. How do you teach a model to do that? 2 stages. First, a cold start. Fine-tune on synthetic, role-specific data so the model learns the language of the protocol, how to write fork and join correctly, how organizer and worker messages look, and how to pass information cleanly. Then, reinforcement learning layers in judgment. The model gets rewarded for correctness, solve the task, for obeying the protocol, no format chaos, and for concurrency, smart overlap without unnecessary waiting. That cocktail teaches not just how to coordinate, but when it's worth splitting or merging, balancing speed against accuracy on the fly. Does it work? On countdown-style puzzles, math reasoning, and Sudoku, Async Think hits a sweet spot. Higher accuracy with lower latency than both sequential chains and naive parallel runs. Why? It avoids the wait for the slowest branch trap and shares useful partial results midway. Ablations show the 2-stage training matters: syntax first, then RL, shaping both reliability and smart scheduling. The coolest part: generalization. Even when trained only on simple countdown data, the model zero-shots the async think behavior on new domains. That means it didn't memorize workflows. It learned a transferable skill: how to organize thought. Accuracy-latency frontier plots make this visible. Async think shifts the curve outward, delivering better solutions faster. Big picture contributions. First, they formalize learning to organize, not just solving tasks, but learning policies that coordinate multiple reasoning processes concurrently. Second, they introduce Async Think, a practical protocol that lets an LLM both manage and execute work via fork/join actions, enabling dynamic, problem-shaped reasoning. Third, they show the gains: accuracy up, latency down, and crucially, that the learned organization skill transfers to new tasks. This reframes LLM reasoning from "how do I think" to "how do I organize thinking?", a foundation for scalable, collaborative intelligence inside a single model. Two roles, one brain. Both organizer and workers are the same LLM under the hood, just operating with different allowed actions. That's powerful. Shared knowledge and style, but role-specific behavior. The organizer decides structure, when to fork or join, while workers focus on solving subqueries and reporting intermediate insights. Because everyone speaks the same mental language, information flows cleanly and the system can explore many shapes of reasoning without extra models or heavy orchestration code. Think of it as one expert switching hats. Planner when needed, specialist when assigned. The figure shows this dance. Dispatching tasks, receiving partials, and merging them asynchronously to build complex solutions efficiently. Key point: the whole organizer-worker protocol is just text. The actions, like fork and join, are emitted as special tags inside the normal token stream. That means you don't need a custom architecture, tool API, or side channel. Any standard LLM that reads and writes text can run this. Why that matters? Deployment becomes trivial. You can plug this into existing chat/completion interfaces. Training is simpler too. The same model learns both what to think and how to orchestrate thinking by continuing the text. And because the control flow lives in the transcript, you get a transparent log of the reasoning structure that's easy to debug, inspect, and refine. It's programming by pros for coordination. Workers are like lightweight specialist threads. The organizer sends each worker a subquery. The worker privately thinks, then returns a compact result when asked. Active just means a worker is currently chewing on a subquery and hasn't handed back its result yet. Input-wise, every worker sees a system prompt, their job description, plus the specific subquery. Output-wise, they follow a simple structure. First, the raw thoughts, their scratchpad, then a short set of takeaways, the distilled signal the organizer actually needs. That split is crucial. The organizer can skim the takeaways to move fast, but still has access to the worker's deeper reasoning if it needs to audit or combine details. This design keeps communication crisp and composable while preserving useful depth. The organizer is the driver. It reads the user's question and produces a single stream of tokens that includes both normal text and action tags. No separate controller network, no external scheduler, just the same auto-regressive process deciding, token by token, whether to think more, fork a subtask, or join a worker. This unifies reasoning and coordination. The model plans as it speaks. The benefit is flexibility. Without extra machinery, the organizer can opportunistically branch when it senses a clean subproblem, or hold off when the problem seems tightly coupled. Because it's all one sequence, the organizer can also weave in context at the right moments, creating a fluid, just-in-time execution plan rather than a rigid, pre-computed workflow. Fork and join are the gears of asynchrony. When the organizer emits a fork, it spins off a subquery to an available worker. That worker starts thinking immediately. Meanwhile, the organizer keeps going, maybe launching another fork, maybe progressing its own reasoning. This is the win. The organizer doesn't stall while workers think. When the organizer later emits a join for that subquery, two things can happen. If the worker is still busy, the organizer waits, synchronizing only at the moment it actually needs the result. If the worker has finished, the returned text gets appended to the organizer's context, and the organizer flows forward seamlessly. Intuition. It's like a chef sending sous chefs to prep ingredients while continuing the recipe. Only when it's time to combine do they pause to grab what's ready. The process ends when the organizer emits a final answer and stops. Big picture. This entire protocol lives at the text interface. No model surgery required. That makes it a unifying lens on how to think. If the organizer never forks, you've got classic sequential chain of thought. If it repeatedly assigns the same query to multiple workers and joins them later, that's parallel ensembling. Async think generalizes both. It can branch only where useful, run branches concurrently, and synchronize at the last responsible moment. The result is a continuum from purely sequential to fully parallel, chosen dynamically by the model. This is powerful because different problems want different structures, and the model can learn to pick the right structure on the fly. Training happens in two stages. First, cold start fine-tuning teaches the model the grammar of this world, how to write organizer and worker traces, where fork/join tags go, and how to format thoughts versus takeaways. Think of it as learning the rules of the game. Second, reinforcement learning lets the model actually get good at the game. It explores many execution structures and gets rewarded for both correctness and efficiency. That pushes it to discover when to split, how many workers to use, and when to wait versus proceed. The key is balancing quality with speed, learning that fewer, smarter branches can beat naive fan-out, and that synchronizing only when needed avoids idle time and wasted computation. Because there aren't ready-made datasets of organizer-worker traces, they bootstrap with synthetic data. A strong model, GPT-4o, analyzes a query and identifies conditionally independent chunks, parts you can reason about in isolation without tripping over missing dependencies. It then generates example traces for both roles following the protocol, the organizer's plan with fork/join placements, and the worker's thoughts and takeaways. Finally, they run rule checks to filter out malformed outputs. Why this matters? Before you can learn clever scheduling, you must first reliably speak the protocol and perform basic decompositions. Synthetic traces provide high coverage, clean supervision for that foundational skill, so later RL can focus on strategy rather than syntax. Interesting empirical note. With several worker slots available, the synthetic organizer traces tend to collapse into two simple patterns. Either interleaving fork and join, so only one worker is truly active at a time, or doing all the forks up front and then all the joins later. Both are easy but suboptimal. This bias is useful to know. It gives a safe starting point, yet leaves plenty of headroom for RL to discover richer, genuinely asynchronous schedules, where multiple workers are active and joins happen just in time. Here's the big picture of how Async Think learns to think like a coordinated team. The same LLM plays two roles, organizer and workers. The organizer reads the main question and decides when to fork subqueries to workers. Each worker thinks independently, returns a takeaway, and the organizer joins those inputs back into its plan. Crucially, this all runs asynchronously, so multiple workers can think at once, pause, or finish at different times, cutting dead time and duplication. Now layer on learning. The organizer's decisions, when to fork, what to ask, when to join, when to stop, are treated as a policy. Reinforcement learning updates the model's weights, so those choices get better over time. What counts as better? Rewards. One reward checks answer accuracy, another enforces clean protocol formatting, and a third encourages useful concurrency, keeping the worker pool busy without chaos. Training nudges the model towards structures that both solve correctly and schedule efficiently. If you only train with one or two fixed thinking patterns, the model becomes rigid. It learns to follow those patterns rather than to organize thinking, so they inject diversity on purpose. During training, they randomly sample an action script for the organizer, like a skeleton of when to fork and join, and include that structure in the prompt. Think of it as giving the model different plays to run. Sometimes it splits early, sometimes late, sometimes it merges often, sometimes it lets workers run longer. This broadens exploration of organizational strategies. The payoff: the model doesn't overfit to a single topology, e.g. always parallelize or always go step by step. Instead, it experiences a spectrum of schedules, which helps the reinforcement learning later discover when each structure actually helps. It's a clever hack to avoid getting trapped in one style of reasoning. First, they teach the model the protocol, how to speak the organizer's language, before teaching it to win the game. Using synthetic query response pairs, The model is fine-tuned with a standard language modeling objective to produce valid fork/join actions and worker takeaways. At this point, it can follow the format reliably, but it doesn't yet know which forks are useful or how to schedule well. That's intentional. Separating syntax from strategy prevents reinforcement learning from wasting effort on basic formatting mistakes and lets it focus on higher-level decisions. Think of this stage as learning the rules and the scorecard so that in the next stage, the model can actually optimize for good team play, rather than just producing well-formed but unhelpful chatter. Now comes the real learning, using reinforcement learning to turn a valid protocol into smart organization. The organizer's choices, when to split work, what to ask each worker, how long to let them think, and when to merge, are treated as actions. The environment feeds back rewards based on both final correctness and how efficiently the thinking was scheduled. Over many episodes, the model discovers patterns like fork early when subparts are independent, wait to join until key signals arrive, or avoid spinning up extra workers when capacity is tight. RL supplies the credit assignment the model needs. It learns which structural moves actually improve outcomes, not just which words complete a format. The result is a learned scheduling policy that adapts to the problem at hand. They design rewards that shape both brains and bones. Get the answer right. Brains follow the protocol, bones, and use concurrency wisely, the athleticism. Accuracy rewards push the model toward correct solutions. Format rewards keep the process well-structured so workers don't collide or vanish. Concurrency rewards encourage useful parallelism without flooding the worker pool. Together, these incentives teach the organizer to act like a good project manager. Set up the right subtasks, keep the team within capacity, merge insights at the right time, and deliver the correct final answer. This balanced reward design prevents the model from gaming any single metric, like over-parallelizing or playing it too safe, and instead promotes robust, efficient reasoning. Here's how each reward shapes behavior. Accuracy reward, the straightforward, did you solve it signal. For single-answer tasks, it's essentially pass/fail. For multi-solution tasks, partial credit encourages the model to cover more unique correct answers, not just repeat the same idea. Format reward, the guardrails. It penalizes mistakes that break coordination. Reusing a subquery index confuses tracking. Exceeding the worker pool capacity, overload. Joining a subquery that doesn't exist, logic error. Or stopping without a final answer, unfinished work. These penalties keep the organizer's orchestration clean and reliable. Concurrency reward, the pacing coach. It nudges the organizer to keep useful workers active, so thinking progresses in parallel while respecting capacity limits. The intuition. Keep the assembly line moving, but don't summon extra hands when there's nothing meaningful to do. This reward teaches the model when parallelism pays off and when it just adds noise. This diagram is showing how they measure how long the thinking truly takes when thoughts split and merge. Picture the reasoning process as a roadmap with forks, new subqueries, and joins when results come back. Between these events are fragments, little stretches of uninterrupted thinking. Critical path latency is the time along the single slowest chain of dependencies through this roadmap. When you fork, multiple branches run in parallel. When you join, you must wait for the slowest branch returning to you. Dynamic programming comes in because you can compute the total latency by stitching together these fragments. Each fork creates subproblems, one per subquery, and each join collapses them by taking the max of their completion times. Breaking the trajectory into before fork, branch fragments, and join lets you compute the overall longest dependent path efficiently. That's the key. It's not about how many thoughts you have, but about the longest chain you can't parallelize away. What counts as active thinking? A worker is active if it's been given a subquery and is currently decoding tokens. With that, the thinking concurrency ratio is the average number of active thought streams over time. Intuition. Imagine a kitchen. If only one cook works while others idle, dinner is slow. If several cooks prepare different dishes at once, you finish sooner, provided they coordinate. This ratio captures how much overlapping work the organizer schedules. It rewards using the workers to reduce idle time and avoid bottlenecks. But raw overlap isn't enough. You need useful overlap that respects dependencies. That's why concurrency is measured over the actual thinking timeline, not just how many workers exist on paper. They normalize concurrency using the critical path latency, T, the true wall clock time imposed by dependencies. That way, the ratio reflects real efficiency during the part of the process that actually limits speed. Then they turn this ratio into a reward signal. The model gets a bonus for keeping multiple workers genuinely active while the critical path is unfolding. The idea is simple. Nudge the organizer to overlap subtasks when it helps, rather than waiting for one worker to finish before starting another. This teaches the scheduler to think like a good project manager, staggering starts, overlapping where safe, and keeping the pipeline full without creating chaos. There's a trap. The model could game concurrency by spawning lots of trivial workers that don't help solve the problem. To prevent that, they cap the concurrency reward with a threshold. Past a sensible level of overlap, extra workers don't earn more reward. This keeps the model focused on meaningful parallelism, not spam. It also acknowledges that predicting the correct answer is harder and more important than simply running many workers. So the system rewards healthy concurrency, but only up to the point where it benefits accuracy and real progress. Putting it together, the total reward for a thinking trace is, if the output violates the protocol, format errors, it gets a penalty. No gaming the system by writing bad messages. Otherwise, the reward combines answer accuracy with a small bonus for well-managed concurrency. The accuracy term drives the model to solve the task correctly. The concurrency term encourages the organizer to time fork/join decisions smartly, start subqueries early enough to hide latency, but not so many that you drown in noise. This balance signal teaches the model to be both right and fast, in a way that respects the rules of the asynchronous protocol. How do you do reinforcement learning when an episode isn't one straight text, but a web of organizer outputs and multiple worker outputs? They extend group relative policy optimization to treat the organizer's trace and its workers, traces as a single unit for reward and advantage. Intuition. The team succeeds or fails together, so credit is shared across all tokens from both roles. But they're careful with bookkeeping. When training the organizer, they mask out the segments that actually came from workers, e.g. the returned messages. The organizer shouldn't be blamed or rewarded for words it didn't write. However, they keep the initial join tags in the organizer's loss, because deciding how and when to stitch worker results back into context is an organizer skill. This setup gives clean, fair credit assignment for a multi-threaded, fork-join episode, stabilizing learning, while teaching the organizer to coordinate and integrate effectively. They test on tasks where splitting work helps, a multi-solution countdown game, math reasoning, and Sudoku. Next, they define how they measure both correctness and speed. Two metrics matter. Final answer accuracy is straightforward. Did the system get it right? That lets you compare to other large language model reasoning methods. The new piece is critical path latency, the minimum time you'd need, even with unlimited workers, because you can't break dependencies. Picture the thinking as a fork-join graph. Many branches can run in parallel, but the final answer has to wait for the slowest prerequisite chain. That longest dependent chain is the critical path. Measuring latency this way isolates the quality of the organizer's scheduling from raw compute. It rewards overlapping independent subqueries and arranging joins so downstream steps never sit idle. Together, these metrics tell you if the model is both smart and time efficient, accurate in its conclusions, and organized in a way that squeezes out unnecessary waiting. Think of depth for asynchronous thinking, like the critical path in a project plan. No matter how many helpers you hire, or how fast your hardware is, there's a minimum time determined by the longest chain of dependent steps. That's what this depth measures, a theoretical lower bound on inference time that ignores implementation quirks. Why care? Because it tells you the best latency you could ever hope for with this reasoning protocol. If your actual runtime is close to this depth, your scheduling is great. If it's much slower, you're leaving performance on the table. This metric lets us compare different thinking strategies fairly across models and machines, since it's measured in decoding steps, not wall clock speed. It's the clean yardstick for how efficiently the organizer and workers coordinate. Picture the organizer-worker trace as a directed, acyclic graph. The organizer writes, occasionally forking subqueries to workers, and then later joining to use their results. Latency spikes happen at those joins if the organizer must wait for a slow worker. The trick in Figure 4 is a dynamic programming pass that computes the overall latency by slicing the organizer's text at each join and asking, how long does it take to finish this fragment, given what's already written and any required worker results? Each fragment's time is the bottleneck between two things: the organizer continuing to write, or the slowest relevant worker finishing and getting back. By accumulating these fragment latencies across joins, you recover the critical path latency of the entire asynchronous reasoning trace. In short, break-it joins, account for waits, add up the longest dependency chain. Here's the intuition behind the recurrence without the math symbols. For each chunk of organizer text between joins, its completion time is whichever is slower, the organizer's own writing up to that point, or the path that goes back to the earlier fork plus the time for the needed worker to answer. That's just the longest path logic in a dependency graph. If no worker result is required, you just count the organizer's writing time. If a join depends on multiple workers, the slowest one dominates. This recurrence unrolls across the organizer's fragments, so by the time you reach the final fragment, you've stitched together all the waits and writes into the single critical path latency. It's a clean, local rule that recovers the global bottleneck. What do those symbols stand for? Think of phi as how much writing the organizer does in this fragment. The join at this fragment points back to a specific earlier fork, that's J, and possibly to one of several subqueries launched at that fork, that's K. Within that earlier fragment, the organizer needed to write enough to set up the fork, F before -fork K. And then the worker needed time to produce its answer, F query K. Those two pieces form the worker branch's cost. At the join, we compare the organizer's ongoing writing versus the worker branch's return time. The larger one wins, because the organizer cannot proceed past the join without that dependency satisfied. Classic Countdown is a warm-up for modern models, so they crank up the difficulty. Multi-solution countdown? MCD. Now, the goal isn't just to hit the target once. You must find exactly 4 different valid solutions. Different means they're not just cosmetic tweaks. Either the numbers used differ, or at least one operation's usage count differs. Why is this great for testing asynchronous reasoning? Because diversity is hard. You're not optimizing for a single neat path. You're exploring multiple disjoint paths without repeating yourself. An organizer can fork workers to probe distinct arithmetic constructions in parallel, then join to filter duplicates and assemble a clean set of 4. The challenge isn't only correctness. It's coverage and coordination. MCD stresses both breadth, exploration, and control, deduplication, the sweet spot for learned scheduling. They build a data set that guarantees real diversity. For testing, each target number pairs with multiple subsets of source numbers that are known to admit at least 4 distinct solutions, so the task is genuinely solvable, but non-trivial. Training uses different targets to avoid leakage, plus synthetic cold start traces where the agent pool is capped at 2 workers, matching the intended runtime setup. One neat detail: an async think trace naturally yields multiple query response pairs, organizer prompts, worker subqueries, and their returns, which becomes training signal about how to split, weight, and merge. The result is a corpus that teaches the model not just what a solution looks like, but how to orchestrate multiple solutions without stepping on its own toes. Training happens in 2 steps. First, supervised format tuning. Teach the model the organizer-worker protocol so it speaks the fork/join language reliably. Then reinforcement learning takes over to actually learn smart scheduling: when to fork, how many workers to use, and when to join. The reward is the fraction of valid, distinct solutions found, perfect for MCD. They use group relative credit assignment, so different trajectories for the same query compete. This helps the model discover better coordination patterns. Capacity is set to 2 workers, so the model learns to budget attention rather than spawning a crowd. Response links are capped and reset at joins, preventing degenerate just think forever behavior and keeping comparisons fair. By the end, the model isn't just formatting, it's timing and routing its own collective intelligence. Baselines probe 2 extremes. Sequential thinking. One model reasons alone, no forks or joins. Great for coherence, weak on exploration. Parallel thinking. Sample multiple independent answers from that sequential model and majority vote the top 4. That adds breadth, but no communication or deduplication during generation. What's missing in both is learned coordination. Sequential underexplores. Naive parallel duplicates effort and can miss coverage or waste time on similar paths. Async think is tested against these to show whether structured, learned scheduling can beat brute force independence and single-threaded depth. The results focus on accuracy for MCD. A prediction counts as correct only if the model returns 4 valid, distinct solutions that meet the rules. This metric rewards both correctness and diversity, not just hitting the target once. It's a tight test of coordination. You need to explore different solution families and avoid duplicates, then package them cleanly. Interpreting the figure, you'd look for higher accuracy and whether the asynchronous strategy closes the gap between the critical path lower bound and realized latency while maintaining solution diversity. Here's the big takeaway from the figure. When a problem has many valid answers, async think is much better at covering them without tripping over itself. Think of the multi-solution countdown task, like searching a maze that has several exits. A naive team sends 4 people down similar hallways, and they keep bumping into the same exits. Async think instead assigns different hallways, and as soon as someone finds something, the organizer updates the plan. That's why, across stricter and looser correctness thresholds, it stays on top. The standout stat is under the strict all correct bar. Async think lands far ahead, meaning it not only finds correct answers, but finds enough distinct ones to satisfy the toughest scoring. The intuition, asynchronous delegation plus on the fly, joins reduces duplication, spreads coverage, and turns partial insights into coordinated progress. What does this metric mean? It checks 2 things at once. Are the returned solutions valid? And are they genuinely different from each other? In multi-solution settings, that uniqueness constraint is key. Repeating a good idea doesn't count. Averaging across multiple random seeds helps ensure we're not just seeing a lucky run. So if a method scores high here, it's not just smart, it's organized, because it knows how to divide the search space and avoid collisions. The strict all correct result is the stress test. Can the model systematically fill all required solution slots with valid, non-duplicate answers? Async Think nails this with a big margin, 89.0% versus around 70% for baselines. Why? Because the organizer continuously redirects workers away from already explored ideas. When a worker discovers a promising pattern, a join action broadcasts the takeaway. The organizer then forks new subqueries that target unexplored regions. That rolling coordination is what majority voting can't do. It only compares outcomes at the end. Async Think, trained via reinforcement learning to time forks and joins, learns to maximize coverage early and reduce wasted effort. The result is not just higher accuracy, but reliably diverse solutions. Exactly what multi-solution problems demand. Why test on AMC 23 and AIME 24? These math competitions reward disciplined reasoning, not just pattern matching. Problems often require chaining multiple insights, trying side paths, and adjusting strategy mid-solution. That's a perfect playground for Async Think's organizer-worker setup. The organizer can probe different tactics in parallel, merge partial progress, and refocus the team. If asynchronous coordination truly helps, we should see gains on these harder, reasoning-heavy benchmarks, not just in final accuracy, but in how efficiently the model reaches a good answer. Training fairness matters. Both Async Think and the baselines learn from the same reinforcement learning pool, DeepScale-R, so any lift isn't from better data. What's unique to Async Think is the cold start corpus. About 43K examples that teach the protocol itself, how to fork tasks, what a worker should return, and how to join concisely. Think of it like onboarding a team. Before optimizing performance, you show everyone how to communicate and hand off work. Once the protocol is ingrained, reinforcement learning can focus on scheduling decisions, when to split, when to wait, and how to route attention, rather than wasting capacity relearning the rules of collaboration. The training recipe reinforces the asynchronous habits that matter in math. First, a quick supervised tune teaches the QN3-4B model the protocol surface, how to format forks/joins, and what a worker's takeaway looks like. Then reinforcement learning kicks in with a cap of 4 agents, so the organizer must prioritize. They sample multiple trajectories per question and use group relative credit. Compare several runs side by side, reward the schedule that solved better and faster, and teach the organizer which actions made the difference. Workers are kept to short bursts, 512 tokens, and that budget resets after each join, nudging the system toward tight, iterative exchanges rather than meandering monologues. The effect: disciplined, modular thinking that's easy to steer. Two strong baselines set the bar. Sequential thinking is the classic chain of thought. One long, linear reasoning trace. It's coherent but slow and brittle. If the early steps go astray, recovery is hard. Parallel thinking runs several independent traces and majority votes the final answer. That boosts robustness but wastes effort because traces can't share ideas or avoid duplicating work. Both baselines are allowed long context for each trace, making them competitive in raw reasoning depth. What they lack is mid-flight coordination. Without an organizer to redirect effort, they can't capitalize on partial wins or prevent the team from crowding the same approach. Async Think wins on two fronts: quality and speed to answer. Even with each worker limited to short reasoning bursts, 512 tokens, the team's organized fragments add up to high accuracy on AIM 24 and AMC 23, matching or surpassing baselines that use much longer traces. The secret is critical path latency. The system keeps the longest dependency chain short by interleaving compact worker updates with timely joins. That means ideas flow quickly, mistakes get corrected early, and effort gets reallocated where it matters. In other words, short thoughts, well-timed, beat long thoughts, isolated. This is the benefit of learned scheduling. The organizer doesn't just think, it manages the thinking process, turning parallelism into real collaboration. Here's the big picture of the math benchmarks. Async think delivers accuracy on par with or better than parallel thinking, while shortening the critical path, the longest dependency chain, by a meaningful margin. On AMC, it edges out parallel in accuracy and finishes faster. On AIM, it matches the strongest baseline's accuracy but still trims latency. Why does this matter? In real problem solving, waiting on the slowest, most interdependent steps is what hurts you. Async think's learned organizer doesn't just spin up more workers, it decides which subproblems can safely proceed in parallel and when to merge, so the organizer isn't the bottleneck. Sequential thinking sometimes looks fast on paper, but it gives up a lot of accuracy because it can't explore alternatives. Naive parallelism explores but wastes time duplicating effort. Async think hits the sweet spot. Targeted exploration, less duplication, and a shorter critical path. This ablation table is the anatomy lesson of async think. Remove reinforcement learning, and the system collapses. The model doesn't learn when to fork or join, so accuracy tanks despite looking busy. Keep RL, but skip the concurrency-oriented reward, and it explores, but poorly. You see fewer useful forks, longer critical paths, and lower accuracy, like a team that talks more but doesn't coordinate. Skip the format fine-tuning, and the model can emit the fork token, yet behaves almost single-threaded. Concurrency ratios stall at simple, rigid patterns, e.g., 50% or 25%, showing it never truly learns to orchestrate multiple moving parts. The takeaway: 3 ingredients are necessary and complementary. Format SFT gives the protocol muscle memory so the model can safely explore structure. The accuracy reward teaches productive reasoning. The concurrency reward shapes scheduling to reduce the critical path, preventing the model from gaming the objective by just thinking longer. A candid caveat: the organizer isn't free. Coordination adds overhead. Think of it as the control plane of reasoning. Even if each worker has modest limits, the organizer's steering, forking, and joining inflate the overall token budget and latency. That's expected. Any non-sequential method that actually coordinates will pay this tax. The key is whether smarter scheduling repays the cost by shortening the critical path. Async think's results say yes. Despite the overhead, it finishes sooner on the dependency chain that matters. This suggests a fair way to evaluate future non-sequential methods. Always account for organizer overhead and judge them on critical path latency, not just raw throughput or total tokens. A fast team isn't the one that speaks the most, it's the one that waits the least on the final blocking steps. Sudoku is a perfect stress test for organization. Lots of local constraints, yet everything must fit globally. Without any Sudoku-specific training, async think beats parallel thinking on accuracy and does it with a shorter critical path. Why? The organizer learns a transferable habit. Break the grid into independently checkable chunks, rows, columns, subgrids. Let workers propose candidates and only synchronize when a constraint truly binds them. That cuts idle time and avoids duplicate work. Parallel thinking starts many threads, but often chases the same spots or conflicts late, wasting cycles. The result shows the learned policy isn't a dataset trick. It's a general method for staging interdependent reasoning, so you explore broadly but converge quickly. They also probe beyond Sudoku with out-of-domain computer science and biology questions. The point isn't domain mastery, it's whether the same forking and joining instincts carry over. The trajectories in the appendix show the organizer still decomposes, routes attention, and synchronizes sensibly. That's the promise of agentic organization, a domain-agnostic skill for coordinating thinking, not a bag of task-specific heuristics. Format fine-tuning is the on-ramp. Without it, the model can technically emit fork/join, but it's timid. It keeps concurrency in simple, fixed ratios and rarely ventures into richer structures. Think of a team that knows meetings exist but doesn't know how to run them. They'll default to one person talking at a time. Format SFT teaches the protocol fluently, so the model feels safe experimenting, spinning up workers for distinct sub-goals, pausing, joining, and resuming. Then reinforcement learning can shape that exploration toward outcomes, higher accuracy, and shorter critical paths. The ablation shows this clearly. Skipping SFT slashes accuracy and traps concurrency at shallow levels. With SFT, Async Think learns to both explore and exploit genuine asynchronous structure. Watch how learning unfolds. At first, accuracy climbs from 0 only by thinking longer. The critical path balloons to the cap. Classic early-stage behavior. When unsure, reflect more. As training continues, the organizer discovers a better trick. Split the work into pieces that can progress in parallel, then join only when needed. You see more forks per query, higher effective concurrency, and the critical path stops growing and begins to compress. In other words, the model shifts from deeper monologue to, quote, coordinated dialogue. The reward design is doing its job. Accuracy incentives push for useful reasoning, while the concurrency and latency signals steer scheduling away from procrastination by reflection. The end state is a disciplined workflow, broad exploration without stalling the final dependency chain. This table is a transfer test. Train on a countdown puzzle. Then, without any Sudoku training, solve 4 times 4 Sudoku. Why is this cool? Because Sudoku needs a very different style of reasoning: constraint tracking, elimination, and cross-checking. Async Think still wins on accuracy and keeps latency in check. Here's the intuition. Sequential thinking is careful but slow to explore alternatives, so it misses solutions. Naive parallel thinking blasts multiple long threads at once, which boosts accuracy but bloats latency because everyone talks at length, often duplicating work. Async Think finds the sweet spot. The organizer learns to fork short, targeted subtasks, then quickly join and reuse those takeaways. That trims redundancy and prevents workers from wandering. The result: higher accuracy than parallel thinking, yet noticeably lower latency, despite being out of domain. This suggests the model didn't memorize Sudoku tricks. It learned a domain-agnostic skill: how to coordinate thinking so it can recompose its reasoning strategy in new environments. Watch the training curves. Like a story, accuracy climbs. The thinking concurrency ratio rises, meaning more useful workers are active at the same time on the parts that actually matter. Forks per query go up, but here's the key: critical path latency goes down. That sounds contradictory until you think like a good manager. Early on, the organizer hesitates. Few forks, long single chain, lots of waiting. As it trains, it learns to fork when a subproblem can be explored independently and to join quickly to recycle insights. More forks doesn't mean more waiting. It means smarter overlap. The critical path, the longest dependency chain, shrinks because the organizer schedules around it, keeping that chain busy while offloading parallelizable chunks. The curves show a shift from think long in one head to coordinate short, focused heads and merge their best bits. That's the essence of learned asynchronous reasoning. More brains at once, less time on the bottleneck. The deeper takeaway isn't just metrics improved, it's why they improved. Thinking is modeled as explicit actions, fork and join, that the model predicts. That gives the learner a control surface. Instead of vaguely, think harder, reinforcement learning can reward concrete coordination choices: when to split, whom to ask, when to merge, when to stop. With those levers, the organizer can adapt its strategy to the task. Branch more when the search space is broad, stay focused when the path is narrow, and opportunistically reuse intermediate takeaways. This action-based structure turns reasoning into something you can optimize, not just lengthen. Overtraining, the model explores different schedules, discovers which ones trim the critical path, and locks in habits that reduce idle time and duplication. That's why you see rising concurrency, more purposeful forks, and shorter bottlenecks. Reward design shapes the thinking style. Remove the thinking concurrency reward, and the organizer becomes timid. Fewer overlapping workers, more waiting, lower accuracy, higher latency. That reward doesn't just say go parallel. It nudges the system to overlap useful work on the critical path, so progress keeps flowing. They also tried a leverage reward. Encourage a fork right after a join, hoping to build momentum from freshly merged insights. Sounds clever, but it backfires. The policy collapses into a rigid rhythm, near sequential thinking with cosmetic forks and joins, because it's optimizing the script, not the substance. The lesson: reward outcomes, not choreography. Concurrency rewards push toward genuine parallelism where it helps. Pattern rewards risk ossifying behavior and killing adaptability. In asynchronous reasoning, the organizer must decide based on problem state, not a fixed dance step. Good rewards create pressure for useful overlap and timely merges without prescribing a brittle schedule. Think of an accuracy-latency frontier as a menu. For a given thinking budget, how good can you get and how fast? By sweeping response lengths, workers for async think, both for baselines, you trace out trade-off points. Async think's curve dominates. For the same or better accuracy, it delivers lower latency, about a 28% reduction versus naive parallel thinking, while still scoring higher on math reasoning. Why? Because the organizer doesn't spend budget uniformly. It allocates words where they cut uncertainty, forking short probes, joining quickly, and avoiding duplicate meandering. Parallel thinking buys accuracy by letting everyone monologue. Async think buys accuracy by scheduling. That means you can dial it, allow slightly longer worker budgets to push accuracy up, or tighten them to beat latency while still staying on a better frontier than baselines. In short, smarter coordination wrings more value out of the same thinking time. This plot is the punchline. The trade-off between how long the bottleneck chain of reasoning takes, critical path, and how accurate the answers are. Each dot is the same model run with a different thinking budget, max response length. Async think lives up and left of the baselines, higher accuracy with shorter critical paths. Why? The organizer doesn't wait for everyone to finish and doesn't spawn redundant efforts. It forks targeted subqueries, pulls back useful takeaways early, and keeps the bottleneck path short. Sequential thinking stays in one lane, so latency grows with depth. Naive parallel thinking opens many lanes, but merges late and repeats work, so the critical path is still long. Learned scheduling, deciding when to fork, what to explore, and when to join, is what bends the frontier. Those dots come from sweeping the max response length, the thinking budget. Across budgets, async think stays Pareto efficient. For the same budget, it reaches more accuracy sooner, and for the same accuracy, it gets there with a shorter critical path. Think of these case studies as popping the hood. The organizer uses fork join as a strategy, not a script. Two patterns stand out: divide and merge exploration, where the organizer continues one line of thought while delegating complementary lines to a worker, and iterative joining, where partial results are merged early to steer what to try next. The key is adaptivity. Forks happen when there's clear upside. Joins happen early enough to prevent drift and duplication. This is how the system stretches the same token budget into more coverage and less waiting, by overlapping the right work at the right time and steering with intermediate facts instead of waiting for full write-ups. In the math case, capacity C equals 4 means one organizer with 3 workers probing different angles in parallel. Picture a geometry problem on a regular tetrahedron. One worker normalizes the edge length, set it to 1, to simplify formulas. Another pursues a vector/coordinate route. A third checks a symmetry or ratio-based approach. These run concurrently. The organizer acts like a hypothesis manager. It checks whether their intermediate conclusions cohere. Do the simplified assumptions and derived relations agree? Only then does it join them back and push the next step. This pattern avoids rabbit holes. A worker can be paused or redirected, and catches contradictions early. Crucially, the critical path stays short, because the organizer keeps the most promising derivation moving while side workers de-risk and supply lemmas. The takeaway from both cases: this isn't reflection or self-correction after the fact. It's structured concurrency. Multiple discipline paths are launched, monitored, and merged with purpose. Intermediate results aren't dead ends. They become steering signals for what to fork next. That yields broader solution coverage, fewer blind spots, higher reliability, consistency checks before merging, and lower latency, short critical path with useful overlap, all from the same underlying language model. Chain of thought is a single-threaded narrative of reasoning. Reinforcement learning with verifiable rewards lets models learn from automatically checkable outcomes, like correct final answers, instead of subjective labels. Async think builds on both, but adds a new axis, learning how to schedule thinking, when to fork, which subqueries to route, and when to join. The reward isn't only be correct. It also nudges efficient coordination, overlap where it helps, merge in time, avoid duplicated effort. That's how a language model behaves like an organized team rather than a lone thinker. Here's the big idea in this figure. You're watching an organizer learn to behave like a smart team, lead under a tight budget of 2 thinking slots. Capacity equals 2. The task needs 4 distinct ways to reach the same target, so coverage matters as much as correctness. The organizer kicks things off by forking a worker with a focused brief. Try multiplication first to get near the target. And crucially, it doesn't sit idle. It continues reasoning in parallel. When a worker returns something useful, the organizer does an early join to integrate progress, tally how many unique solutions are still missing, and immediately redirects effort to the gaps. That's the rhythm. Fork with a targeted angle, overlap thinking to avoid idle time, join early to steer. Notice the diversity strategy. After early wins, the organizer launches a new subquery with a different anchor, start from 89, to avoid duplicating patterns and to broaden search coverage. When momentum slows, stuck, it issues one last targeted fork rather than blindly grinding. Finally, it verifies distinctness and correctness. The takeaway? Learn scheduling, not hard-coded rules. Lets the organizer keep the pipeline full, diversify exploration, and converge faster, even with just 2 concurrent thinkers. Big picture. Giving models feedback that you can actually verify is rocket fuel for reasoning. Think of it like grading math homework with an answer key instead of vibes. Recent verifiable supervision shows big gains because the reward says, concretely, this step/result checks out. The catch is designing those verifiable rewards for messy, open-ended reasoning. It's easy to verify a final number. It's hard to verify a chain of thought, partial results, or nuanced judgments. So researchers try model-based verifiers, reasoning reward models, and co-evolving the generator with the rewarder. Each adds signal, but also risk of being gamed or drifting. Meanwhile, there are many policy optimization flavors: critic-based, critic-free, off-policy. But in practice, The bottleneck isn't just the optimizer. It's getting reliable, scalable reward signals that align with real reasoning quality. Async Think fits this story. To teach coordination and scheduling, you want rewards you can trust. Correctness, good joins, useful concurrency, not just longer monologues. Parallel thinking, spinning up multiple reasoning traces and then aggregating, often helps, but it leaves a lot on the table. Without smart coordination, branches duplicate work, miss coverage, or waste time waiting for each other. Some projects speed up decoding itself or imitate fixed algorithms like DFS/BFS, but those rules don't adapt well to open-ended tasks. The key leap is to learn when to branch, what each branch should do, and when to merge insights. That's the organizer's job in Async Think. Imagine a good meeting facilitator. They don't just say, everyone brainstorm. They assign distinct angles, check in early, and merge partial progress to redirect effort. That cuts the critical path, the longest dependent chain, so you get faster, better answers. Compared to naive parallelism or majority voting, learned orchestration can start new lines of thought midstream, diversify subqueries on purpose, and join at the right moments to avoid redundancy and steer toward a coherent solution. Multi-agent systems show a simple truth. Teams beat lone wolves when roles and coordination are clear. With large language models, people have built teams, planners, solvers, critics, that debate, verify, and iterate. Recent work adds smarts. Agents can update beliefs about each other, swap roles, or evolve together. Add a central controller, and you get tighter plans and fewer dead ends. And with reinforcement learning, the system can learn when to orchestrate, not just follow scripts. Async Think channels the same spirit, but keeps it lightweight. It makes a single model behave like an organized team through a text protocol. The organizer delegates targeted subqueries, workers explore, and joins integrate partial progress. You get the benefits of specialization and cross-checking without a sprawling, brittle multi-agent stack. The lesson across this line of work: structure and learned coordination unlock collective intelligence, especially when the system decides how and when to collaborate, not just that it should. Two scaling levers matter. First, quantity. What happens as you go from a handful of workers to hundreds or thousands? Expect a scaling law. Accuracy improves, and latency per answer can drop until coordination overhead bites. The organizer must keep the critical path short while keeping many workers busy with non-overlapping tasks. Second, diversity. Instead of a uniform pool, imagine a marketplace of expert workers: math, code, data, retrieval, each with tools like interpreters, databases, or web search. Now the organizer's job becomes routing. Who should tackle which sub-problem, with which tool, and when to merge? Think of it like scaling a startup. Hiring more people helps only if you design roles, handoffs, and review cycles. Research here means learning policies that juggle coverage versus duplication, tool costs versus benefits, and early joins versus deeper exploration, so the team gets faster and smarter without tripping over itself. Recursive organization turns workers into managers of managers. Any worker, upon hitting a chunky subproblem, can promote itself to a suborganizer, fork a small team, and run its own mini-plan. This builds a hierarchy, like a tree of task forces, great for deep problems where you must test lemmas, branch on cases, or explore multi-step strategies in parallel. Why it helps? Local coordination happens close to the problem, reducing bottlenecks at the top. The top-level organizer focuses on high-level routing and final integration. The hard parts: preventing runaway branching, deciding depth limits, and passing the right context and expectations down the tree. You also need discipline joins to bubble up only distilled takeaways, not raw sprawl. Done well, recursive delegation mirrors how human organizations tackle complexity: break it down, delegate authority, summarize upward, and keep the main thread moving. Humans in the loop? can supercharge the organization. Two natural roles: human as organizer and human as worker. In the first, a person uses the fork/join protocol to direct a fleet of artificial intelligence workers, assigning angles, setting priorities, and performing early merges for alignment or safety. In the second, the organizer can fork tasks to humans when judgment, domain expertise, or real-world context is required. Verify this clinical implication. Assess the ethics. Check this data source. The key is a clear interface. What context does the human receive? What format do they return? And how does the organizer weight and integrate that signal? Get this right, and you blend machine-scale exploration with human discernment. Open challenges: avoiding overcalling humans, rewarding useful interventions, preserving privacy, and keeping latency low. But the payoff is big. A collaborative system that knows when to ask for help and how to use it. Big idea here. Let humans and artificial intelligence co-design the plan before the async thinking starts. Think of it like drawing the playbook together, then letting the team run it at high speed. In practice, the human sets the agenda: what to fork on, what interim facts are worth joining early, what counts as a proof or a stop condition, and how much budget to spend exploring versus verifying. The organizer, the model, then executes that plan, forking workers to cover strategies the human cares about, and joining at pre-agreed milestones to check progress. Why this matters? Pure autonomy wastes cycles on guessy detours and duplicates. Co-planning injects domain knowledge, risk tolerances, and success criteria up front. You get faster convergence and fewer dead ends, without putting the human in the critical path for every micro decision. Good templates, defined subgoals, validation checks, time caps, and escalation rules. When to ping the human. You end up with a hybridized intelligence: human judgment steering, artificial intelligence scaling, organized, verifiable, and efficient.